What's going on, everybody? It's Dan from SageMathTutoring.com, and we have a quick video about the Poisson distribution, which is something that comes up in statistics courses. And basically, there's two main things to talk about when it comes to the Poisson distribution. First thing is that it's a way to find the probability of a certain amount of occurrences happening within a given time interval. So, for example, let's say you know the average amount of occurrences of rain in a year in Seattle. Let's say it rains, maybe 300 times a year or something, because in Seattle it rains a lot. So maybe you know that the average amount of times that it rains in a single year is 300 in Seattle. So then what you could do is you could use the Poisson distribution to figure out, well, okay, well, what's the probability then that it will rain two times per year, right? So obviously that would be very low, but that's an example of how to use the Poisson distribution. Now, it is also the case that if you sort of satisfy certain parameters, which perhaps I could discuss later, but if certain parameters are satisfied, you could also use the Poisson distribution function, which is right here, to sort of estimate the binomial distribution as well. So sometimes you're going to have problems where the binomial distribution formula is going to be a little bit too complicated and cumbersome to calculate with the given information from the problem. And in that case, you could just switch over to the Poisson distribution. Okay. And again, that depends on whether or not some criteria are met. But we could say the main purpose for the Poisson distribution is the first thing I mentioned, which is to calculate the probability of a certain amount of occurrences within a given time interval. Now, despite the fact that this function formula looks kind of annoying because, first of all, it's using lambda symbols instead of the mu symbol, which is something my student at home is probably really used to. Um, Typically, probably up to this point, you're used to the mu symbol representing the mean value. Well, in the case of the Poisson distribution, they've decided that they're going to use a lambda symbol instead. Okay. Now, the lambda in this context means the average amount of occurrences in that given time interval. And then the x in this case represents, how many occurrences we're sort of analyzing to see what the probability of those occurrences would be in that given time interval. So anyway, that's a little bit of a word salad right there. But let's bring it down to earth with this problem right here. So it's actually a very easy problem, I would say. Um, in an urban county, healthcare officials anticipate that the number of births this year will be the same as last year when 438 children were born. An average of 438 divided by 365, or 1.2 births per day. So the time interval we're actually looking at right now seems to be days, but let's take a look. Daily births have been distributed according to the Poisson distribution. What is the mean of the distribution? Well, that would be 1.2, okay, because we're looking at days as the time interval. We're looking at days as the time interval. As you can see, any given day, we're looking at days as the time interval. So the average amount of births per day is 1.2. So that's actually given in the problem. Okay, so looking at the next question. For any given day, what's the probability that no children will be born? So in other words, replace x with 0. So we are looking at 0 for x. So let's find p of 0. And that's going to be, now we already know the average, the mean, so lambda can be replaced with 1.2. So we're looking at 1.2 raised to the 0 power times e to the negative 1.2, and that's going to be all over 0 factorial. Now, hopefully my student who's watching this from home, you got 1.2 raised to the 0 power, so that's just going to be 1. Hopefully my student understands that anytime you raise something to the 0 power, it's just going to be 1. We have e to the negative 1/12, which I'm just going to rewrite right now because I don't want to kind of do too many moves at once. So we're just going to rewrite that right now. Now, hopefully my student who's watching this recognizes that 0 factorial is also 1. So that's something worth knowing. Okay, and then we have the fact that this, of course, would be 1 over e to the positive 1.2, and that turns out to be approximately 0.3. All right. So the probability that no children will be born is um, 0.3, also known as 30%. Okay, so that actually seems reasonable. And even if you look at the graph that the professor provided, the bar here, we're at 30% there, aren't we? And that kind of, makes sense. I mean, if it's the case that an average of 1.2 births per year occurs or per day occurs, well, it's not that much of a stretch to say that 0 births might happen in any given day, right? So 30% seems pretty good to me. Calculate each of the following probabilities. Okay, so it's going to be the exact same process. You're going to plug in 1 and you're going to plug in 2. So I think my student probably is already getting the hang of this. This is not a big deal. A lot of it just has to do with knowing, what kind of a problem you're going to need the Poisson distribution function for. That's sort of step number 1. And step number 2 is to not get freaked out by the lambda symbols or the factorial symbols, or even the e for that matter. I mean, the e is just a special sort of constant. It's a very famous constant in mathematics that shows up. It's essentially 2.7. But it's kind of like pi, where it's like a famous constant. So anyway, looking at this one, let's actually do it. So we're looking at p of 1, and that would clearly be 1.2 to the first power times e to the negative 1.2 once again. And then we're looking at 1 factorial. Now, 1 factorial is just 1, so I'll write that underneath. 1.2 is clearly just 1.2. I'm going to leave that up top. Now, let's get this over with. The e to the negative 1.2, that goes down below. So we're going to have 1 times e to the 1.2. Down below, when you calculate that, that turns into approximately 0.36, which is about 36%. So that is the probability that there is 1 birth in a day. Now we're going to look at the probability of 2 births in a day. So we have p of 2. So we have 1.2 raised to the second power. We have e raised to the negative 1.2. And then we have that all over 2 factorial. Now, 2 factorial in this case is going to be 2 times 1, which is just 2. 1.2 squared, that happens to be 1.44. And let's get this part over with. We will have e to the positive 1.2 down below. And when you put all of that in your calculator, you end up with, let's see, approximately 0.22. Okay. So a little bit less likely for there to be 2 births in a given day. Okay, so then they ask, what is the probability that no more than 1 birth will occur on a given birth? So when they say, what's the probability of no more than 1 birth, what they're saying is, what's the probability of either 0 births or 1 birth? And that's going to be really easy because all you have to do is just add the probability of 0 births, which we already found right here, and we're going to add that to the probability of 1 birth, and we already found that as well. That is right here. Okay, so 0 births is the blue rectangle, and 1 birth is the green rectangle. And since these are mutually exclusive events, meaning it's impossible for there to be simultaneously 0 births on Tuesday and 1 birth on Tuesday, right? That's impossible. So those are mutually exclusive events, and whenever you have mutually exclusive events in probability, if you want to know what the probability of one thing happening or the other thing happening, well, then you just add the probabilities. So I think you understand that would turn into, um, 0.3 plus, what is it, 0.36, and that is most definitely 0.7. 66. Okay, so 66% when it comes to that. All right, so hopefully that makes sense. Now, that would be a matter, if you're looking at it graphically, that would be a matter of adding the height of this bar plus the height of this bar. Okay. So like I said, it's going to be a quick video on the Poisson distribution for my student who's watching this. Like I said before, really, you just need to recognize that lambda means the average amount of occurrences on a given time interval, and you have to just realize that that's what lambda means, and also to just realize what kind of a problem you're going to need it for. It's basically finding the probability of a certain amount of occurrences happening in a given time interval. Now, obviously, you have to be very clear about what the time interval is, right? In this case, we knew that it was days, right? So that's one thing you really want to hone in on right away. It wasn't years, right? It wasn't weeks. It was days. That was the time interval. And the reason you need to be savvy about that is because, they did mention year, right? But you can kind of see we're looking at days as the unit of time that we're analyzing in this particular problem. Okay. So hopefully that's helpful, and I will talk to you later. Take it easy. Bye.